This is one of a series of lectures produced by the Further Mathematics Support Programme, for a revision for Edexcel, in this case FP1 module, and we're looking in this session at numerical solution of equations. The specification says that we're looking at solving equations of the form f of x equals 0, so we're looking for the roots of equations, and it does also specify in there, because this is an AS module, then the functions involved will be in C1 and C2, so essentially they're going to be polynomial type equations. So we're looking at, if this is the x-axis, looking for where does the graph of y equals f of x cross the x-axis. In other words, looking for this point here. This is the root that we'd like to approximate. So in general, these methods can be used for things that we can't solve algebraically, although many of the examples that you'll be asked to do will be ones that could be solved algebraically. Usually questions will start off by asking you to prove that a root lies in a particular interval that you're given, the interval AB that I've looked at in here. Now, to do that, you have to go through a series of particular things. First of all, find the value of the function at a, f of a equals f of b, then in other words at the other end, and there should be a change of sign. So one of these will be positive and one will be negative. To gain the marks in this first section, you must say that change of sign, so you must note that there is a change of sign, implies that there's a root in the interval AB, and it's quite satisfactory to use the notation for an interval as such. So you won't get marked if you simply say f of a equals f of b equals and then say therefore there's a root in AB. You must make or note the fact that there is that change of sign to gain the marks. The other thing I'll say is that efficient use of calculators in this particular section can save you time. In particular, if you're asked to do iterations of these things over and over again, then the use of the answer button to represent x in an equation can help you a great deal. So particularly when you're doing multiple iterations. Although having said that, many of the questions you'll be asked to do will only ask you to do each of the techniques once. The particular techniques that you're asked to look at are interval bisection. I'll just quickly run through the basic ideas of these. Interval bisection, perhaps the simplest of these, says that if we have a root in an interval AB, then the next thing to check is the midpoint of that, hence the bisection, A plus B over 2. These are often done by tabulating, so that you'd have a table of x values, for example 2 and 3, and calculate f of x, and then go on to 2.5, noting perhaps, for example, this would be positive and negative. Then if you found that the 2.5 was negative, the root is now in the interval 2 to 2.5, because the change of sign takes place within that interval somewhere, or at least the 0 is there, and therefore you then go on to the midpoint of that 2.25, and you repeat that as often as necessary depending on the particular question. The second technique which is required is to look at what's called linear interpolation. Now, linear interpolation, as the name suggests, is saying that instead of the function being a curve, which it will in general of course be, if this is the x-axis, we've got the function looking like this between our values a and b again, then we're going to assume that it lies as a straight line between these points here. So there's my y value on the function at b. So we're going to take this to be a straight line. And if we do that, then we can calculate this value here, let's call it alpha for the root, by looking at the similar triangles that are produced by that straight line. So the similar triangles are in here, and the one which is above the axis here. Now, as they're similar triangles, we can use ratios of sides. So the ratio of this side here, which will be alpha minus a, so we get alpha minus a divided by the height of this triangle. Now, if that is at a, the y value will be at f of a. Now we need to put in a modulus here, so f of a is the height of the triangle. It could be positive, it could be negative, depending on the function, of course. So we'll put in mod f of a. So that's one triangle dealt with. The other triangle, simply looking at the side, again the corresponding sign here, b minus alpha for this one, and then the height here is at f of b. Now again, I need to put in the modulus so that we get modulus of f of b. The reason for the modulus there is you don't know, and the diagram is simply looking at a generic type of diagram. It depends on the function whether it is positive or negative. So that's linear interpolation. The third method that you need to look at is NewtonRaphson. Now the NewtonRaphson process, as I'm sure you will remember, is one where we're looking at the tangent to a particular point on the curve. So it's my curve. If I now take the tangent here, then NewtonRaphson says, well, if this was an approximation to the root here, let's call it xn, then this point is a better approximation, xn plus 1. And by using the gradient of this is the tangent, the gradient of the tangent f dashed of x is equal to f of xn, so I should say f dashed xn is the height here, f of xn, divided by this side of the triangle, which is xn minus xn plus 1. So that's the method. It looks at using the tangent and rearranging that. Xn plus 1 is equal to xn minus f of xn divided by f dashed xn. So those are the three methods. Now the only one that the formula sheet looks at is the Newton-Raphson, and this is from the formula sheet that you're given in your exam. So you'll see that there's the Newton-Raphson equation written out in the form I've just been talking about. Xn plus 1 is equal to xn minus f of xn over f dashed xn. Right, now going on to look at one or two examples, well, examples of each of these sorts, to show you the sort of thing you might be asked to do in exams. So this is the first question then. We need to, this idea is show that the root is between certain values. Well, as I said to you before, this is a case of working out the value of the function at each end. So f of 1 actually turns out to be -1. F of 2 is 8. And then a change of sign, so you note that here there's a change of sign implies the root is in the interval 1, 2. So that's sufficient. But you need both of those statements there. The change of sign implies must be in there, the root, to get the A mark here. The marking for that is M1 for calculating f of 1 and f of 2, and A1 for getting both of these comments in here, or the change of sign and then implying that the root. The second part of the question says use interval bisection twice to find an interval of width 0.25. So this time then, well, we must go for the midpoint, f of 1.5. That turns out to be 2.696. Importantly, it's positive, and so the root is now in the interval between 1 and 1.5. So it's changing sign between f of 1, which was negative, to f of 1.5, which was positive. So the next value to change, to check, is 1.25, the midpoint again, and f of 1.25 comes out to be 0.698, again positive, so that our root is now in the interval from 1 up to 1.25. And that's all that's necessary to answer that second part of the question. The marking here, there's a B mark for calculating the f of 1.5. It then gives a method mark for realizing that you then need to check 1.25, and an A mark, A1 mark for getting the interval of the correct size. Well, the correct interval rather. This next question was actually a two-part question dealing with this function. I'm looking at it in two parts because the first part of the question asks for linear interpolation. We'll see in a second that the second part is to do with NewtonRaphson. What I suggest you do with linear interpolation, as we're doing here, you'll notice, in fact, first of all, is that we have to use it only once. This is quite usual in linear interpolation questions, in that the arithmetic can get quite tricky in these. It's not particularly difficult in terms of the technique, but the arithmetic can. What I suggest you do is you draw a sketch of what's going on here. We're told that it lies in the interval 1.6 to 1.8. So we'll check exactly what the value of 1.6 is in the moment. In fact, I know it's negative. It doesn't actually matter at the moment because we'll get the same sort of calculation. And we're going up to 1.8. So there's my diagram. And what we're trying to find is this point here. This is my value of alpha that we're asked to find. We need to check f of 1.6. So first of all, let me do that. F of 1.6 turns out to be negative 1.295. I'll put a few more. It's actually an important point I'll come back to in a second, but it's 1.295438081. Well, you can note that down if you wish on your calculator, from your calculator. F of 1.8 is 0.540186. Now what we want to do then is to use this idea, well, we've got this height here, so we want alpha minus 1.6 divided by the height of this triangle. Well, that's going to be 1.2954 is equal to 1.8 minus alpha divided by 0.540186. Now exactly how many decimal places you use at this point doesn't really matter, as long as you use sufficient. If we're asked to do 3 decimal places, then at least 4 decimal places required in your calculation if you're not going to use the full value of the function in your calculator. Rearranging that equation to get alpha, let me do a little bit of work on it. We need to multiply by the 0.54 is equal to, and then the 1.8 minus alpha multiplied by the 1.295, so 40186. Rearranging that to make alpha subject produces alpha equal to 1.741. And the only thing to take care of there is the fact that alpha needs to be given to 3 decimal places. Therefore, you need to use sufficient decimal places in your answer. This is a continuation of that question, and you can see it's NewtonRaphson this time. Well, NewtonRaphson, the first thing we need to do is to find the derivative. So this particular one, f dashed of x is equal to 10x minus, so 10x, and then minus 6x to the half. So multiplying by the 3 over 2. 4 times 3 over 2 is 6, reducing the power x to the half. The differentiation there gains its marks, just simply a method mark for showing that you can differentiate correctly with either of these, and then an accuracy mark for getting the whole thing correct. So this is a M1 mark and an accuracy mark here. The NewtonRaphson method then, so we can quote. So we want to find a value of alpha. We've got to just do once, a second approximation, implying that we've got to use NewtonRaphson once. So that alpha is going to be equal to our value of xn minus f of xn divided by f dashed of xn. Remember, you can look that up in your tables. So substituting the values then, this is 1.7, and then minus, I would always put a bracket round these things. So on the top line I've got 10 multiplied, I beg your pardon, the top line is the function, so it's 5 multiplied by 1.7 squared minus 4 multiplied by 1.7 to the power 3 over 2 minus 6. Put a bracket round that just to remind yourself when you're using a calculator in a second, and also around the bottom line here, 10 multiplied by 1.7 minus 6 multiplied by the root, so 1.7 the power half, either power half or square root, depending how you're using a calculator. Now it is then very much calculator work, and this turns out to be 1.7453. So alpha is 1.745 to 3 decimal places. The marking there comes from a method mark sorry, B marks first of all. These are marks which don't have any method associated with them. You get B marks simply for calculating these two values here. So 2 B marks there. There's then a, beg your pardon, we've gone back a slide. There's then a okay, I'll just look at the marking here again. So in the Newton-Raphson, we've got B marks for calculating f of 1.7 and f dash of 1.7. So there are B marks for doing the calculations here. If you've not done them and written them out as I've done in a calculation, then don't worry. You will pick up the marks then by a method mark and a mark here. Going back to the slide before, the marking here, similarly done, B marks for f of 1.6 and 1.8, and then a accuracy method and accuracy marks for writing down here method and accuracy in exactly the same way as the question following. Okay, that's the end of that particular session, looking at a numerical solution of equations for FP1. Other sessions are produced for the rest of FP1 units, and in fact other Edexcel units, and also for other boards should you wish to find them.